So it's my pleasure to or honor to introduce Professor Peter Hinterdorfer. Peter is from, as you've seen in the program booklet and everything, from Hannes Kepler University in Linz, Austria. And I think in 90s, Peter and his team pioneered AFM, tip functionalized AFM, making measurements with, antibodies, antigen, and attaching proteins to tip with linker molecules, as we were talking yesterday. All of this started in his lab in around 93, I think, right, Peter? 93 is the first time we pulled a ligand receptor.
93,
Yeah.
then finally was published 96. So
Yeah, sometime, yeah. So it's the first one in AFM history. I think Peter will have 3 lectures today, and then in tutorial we will again have question answer kind of a session just like yesterday, and then half the lab will go to see the just like yesterday. Half of you will go to the lab, and half will stay here for question answers and other things. Okay.
Okay. Yes, good morning. I'm really glad that I can teach here at the Giant course, and I think we should thank Shiva that he was able to set it up. We were talking about it yesterday, and it's a very competitive project, and with a success rate of 20%, and so we really should thank Shiva for organizing it, and thanks also for the invitation and your kind introduction. So my name is Peter Hinterdorfer, but please call me Peter throughout the course. And we'll spend quite some time. And I would also like to encourage you to interrupt me during my talk. It's nice if you take a little bit of my speaking load and also contribute. And I think it's nice to have a conversation. You know, it should not be like a lecture from the front. Okay. Let me first of all tell you a little bit where I come from. So this is Linz, Austria. It's between Salzburg and Vienna in a way. And you may say, okay, tourists visit there when they get lost on the way between Salzburg and Vienna. And this is a landmark of Linz. It's a kind of church on a hill. Yeah, that's winter. You see that we have also some snow in winter. And our university was founded in 1967, so it's a very new university. And it is the Johannes Kepler University. And Johannes Kepler, actually, he used to live in Linz from 1612 to 1627. He contributed there with the second Kepler law, which is the kind of, the time the planets circulate around the sun and the long axis of the ellipse. And also he composed more philosophical work, the Harmonices Mundi. But you may, if you look at the times, you may recognize that there's a little bit of gap between the leaf of Johannes Kepler and the Johannes Kepler University. And you may ask, what has our university, how does it connect to Johannes Kepler? And I can tell you, not at all. He was teaching, of course, at these times, scientists were even poorer than we are now. And so he was teaching at the agricultural school, and obviously not at the Johannes Kepler University. And I think it was just a clever move of our PR department to just take the name without asking him. So that was not possible anymore. What maybe is the most famous part of Linz is the Linzer Torte, so it's a tart, because it's literally the world's oldest known cake. And was documented as early as 1696. Yeah? So if you hear about the famous Viennese pastries, forget about it. It's a Linzer Torte that is famous. And I also heard that even in other countries, so if you are learning bakery, then the first cake, what you are preparing is the Linzer Torte. So it's kind of really historical. Okay. So, you already heard yesterday a lot of AFM, and I'm supposed, and you know that it is an imaging technique that is atomic force microscope that was invented to image single atoms on the surface, and this is also what it gives the name, so atomic force microscopy. And the traditional mode is the contact mode, which in principle acts like a record player, but I'm not sure if you know how a record player works, because I don't think you have one at home. I still have, yeah. So it basically scans across the surface and follows the surface topography. And this is the first invented mode of AFM. And why AFM is so important in biophysics and biology is because imaging can be done in physiological conditions, yeah, so in aqueous conditions. And this is not the case with other high-resolution techniques in biology, like electron microscopy. You have to freeze or put a vacuum on, or X-ray crystallography. You have to, grow crystals and whatever. But AFM can be done in aqueous, in physiological conditions, and this makes it so attractive for biology. However, the contact mode can be destructive for biological samples because they are soft and they are also moving. And this is why a tapping mode has been invented, which is an oscillatory mode. So basically the cantilever oscillates, and you are using the oscillation amplitude as a feedback signal. So that is very often used in biology. And I will also talk about this in more detail. And actually, the measurement mode we're starting is measuring forces. That goes back, if you want, to Isaac Newton. He was measuring gravity with a spring. So of course you have the Hooke's law here, where the force is a spring constant times extension of the spring. And the cantilever of an AFM is basically, it's a Hookean spring. So AFM can also be used to measure forces. And this is actually also the mode that we were starting in with. And this is what you see here. So you can, for instance, measure tip surface forces if you approach with the tip to the surface. We can see here, this is first no interaction, horizontal line. Then the cantilever indents into the surface, it bends up and is subsequently withdrawn. And if there is adhesion of the tip to the surface, you get a force signal like this, and you can measure adhesive forces of tips to surfaces. Yeah, so this is more for surface chemistry. And this can also be used on the single molecule level. So for instance, you can unfold proteins, you can push your tip into a protein and pull on it, and this is the unfolding force that is measured, can be measured as a strength of intramolecular interactions. I will come to that in more detail, but just to give you a taste, what will my talks be about it? Yeah, and I also want to say that we are organizing a winter workshop in the winter school. So the talks I will present is also somehow a little bit of a collection of this winter school. And this is why the authors are, there's always a second author on, who were preparing the talk for the winter school. And in this case, it was Eugene Oshie will also come here tomorrow. And I would like to go a little bit more now with AFM into biophysics, but still present a little bit also of the early history. So, I mean, where are we now? Somehow we are on a central meeting point. We are now in a time where sciences are working together. So we have physics, molecular biology, chemistry, inorganic, organic, supramolecular structures, and we all meet each other here. And of course, it also has to do with sizes. Yeah. So what are we able to image? This is from the macro size, and this is also a little bit the development of biology. Of course, you can see that here it comes from the macro to the micro and to the nanoscale. So now we are interested in proteins and atoms, for instance. And of course, it's also a time development. You can see that here. And this is also what the whole workshop here is about, to kind of connect sciences to each other. And Something happened with my computer. Okay, sorry about that. Okay, and it has to do with dimensions, of course. And if we are talking about AFM, then of course we are talking about nanometers. And of course you are aware of what a nanometer is, but just let me put it on a simple example of skin here. Of course, we can just see hands and then also get more detailed into the skin, like with optical microscopy. And then if we are coming to, 100 microns, that's certainly something what you can see just with simple optical microscopy. We can also look at blood cells, and if you go down to micrometer, 100 nanometers, we can image DNA, 10 nanometers, and now we are able to image even single atoms, for instance, also with the atomic force microscopy. So with the development of science, we could, of course, scale down the dimensions where we can look at it. And this is now scanning probe microscopy or atomic force microscopy. So that was also one of the techniques. I mean, electron microscopy, of course, was invented earlier, where we are not using light as a source, because optical microscopy was, of course, the traditional technique in biology that was used already early on. But we can overcome the diffraction limit of optical microscopy with AFM, and that is, of course, very important. So we are able to watch things on a nanometer scale. And we can also, this is what I try to emphasize with the force measurements, we can also feel and touch with the AFM, so not only image. And it was kind of, tunnel microscopy was invented in 1981. Gerd Binnig and Heinrich Rohrer, and they received the Nobel Prize in Physics in 1986 for that. And I think I don't have to go into the details. This is what I'm sure Shibat already explained to you yesterday about the basic principles, but you need a detector for it. And I think Shiva was also talking about different detection methods yesterday. In biology, mainly the optical path is used there because you want to image in liquids. And we have a feedback controller, a scanner, a computer, and this is how we can obtain a topography image with AFM. And so just to very shortly take a look back, scanning tunneling microscopy was the first one. And it's based on the quantum tunneling effect, where a small bias voltage is applied, and then that it's not in contact, but the tunnel effect is used to sense the distance of the tip from the sample, and this is how the first non-optical microscopy technique besides electron microscopy was invented. And so this is, again, you see here this tunneling electrons, and this is how the distance can be maintained, and how the topography relief of a surface can be imaged. But of course, in the case of scanning tunneling microscopy, you need a kind of conductive sample, otherwise you cannot do that. And that is, of course, not always the case in biology, so you don't really have conductive samples. But then, and it is like tungsten and so on, and we know that there's an exponential distance dependence of the tunneling current, and this is how the distance can be maintained. And you can use a feedback loop then, so either you hold a constant distance and measure the tunneling current, or with a feedback loop you can follow with the tip the surface topography, and in this way you get as a resolution on the atomic level. And these are just a few of these famous historical examples that were measured at this time. So iron curls and FE rings and so on. So that is the scanning tunnel microscope. And then AFM came then a little bit later, but actually the first detection method of AFM was also with tunnel current. So I mean the surface was mechanically sensed, but the distance was also measured with the tunnel current, which was the first approach. But then in this way one could start to image isolating materials with the AFM, which is not the case for tunnel microscopy. I mean, there's always way to overcome it a little bit. So even you can use hydration layers that are also in a way a little bit conductive. But that is how it came then from the tunnel microscope to the AFM. And the AFM, as already mentioned, works of course in air and vacuum, but also in liquids and molecular resolution. Yeah, and atomic resolution is actually only possible with atomically flat samples, yeah, because then it is also called the imaging atom on the tip. Yeah, if one atom at the tip end does the imaging job, otherwise you don't really get atomic resolution. And that is not the case in biology. It's because they're samples, they're not atomically flat, and they are also moving, they are soft, and we don't really get atomic resolution with, maybe with DNA, but with proteins or whatever. It's maybe sub-nanometer resolution, but not atomic. And also important, the AFM is a force measurement device for inter and intra molecular forces in the piconewton range. Okay, so yeah, that is yeah. For AFM, it must not be conductive. Yeah, it doesn't have to be conductive. Yeah.
But if you're using liquids, then the liquids which are around the tip, those will be conductive, right? Actually, first of all, I'm not getting why it should not be conductive.
No, it can be conductive, but it doesn't have to be conductive. Yeah. But it doesn't have to be conductive. If for STM, it has to be conductive. Otherwise, you don't.
Yeah.
Okay.
Okay. Oh, got it.
It doesn't have to be conductive. Yeah.
Okay.
It can be conductive, but doesn't have to be conductive.
Okay.
Yeah.
Yeah.
Because there's also electric AFM and so on. You can also use electric forces with AFM.
Yes.
And there has to be some, but AFM just also works purely mechanical. Yeah.
Okay.
Yeah. So it doesn't have to be conductive.
Yeah. Thank you.
Sure. Okay. So yeah, that is a little bit of a comparison now of STM and AFM. You can see that was the early design. Crystalline structures, of course, you get the best resolution. And yeah, of course, it has to be flattened and clean to get atomic resolution. AFM works on any surface. There's also some derivatives of AFM where you can use also electrical magnetic forces, thermal forces also play a role, of course. But it's more a mechanical measurement, and I will also come later a little bit to what artifacts we can get with AFM. Okay, and of course the tip size is of course also an important point because it somehow also determines the resolution, but the material properties are not so much an issue. It's basically just it's the size of the AFM tip which determines the resolution. And this is now a little bit of a comparison of AFM with other techniques that are used in biology. So optical microscopy, of course, is limited to the Abel limit. You don't have sample damage. There is, unless the light intensity is that high. And of course, optical microscopy can also be done in physiological conditions, so you can look at living samples. Electron microscopy, of course, you need a vacuum, so you need to freeze it or dry it. You get a better resolution with, and in particular, cryo-EM really has made a lot of progress in the last 20 years, and somehow has replaced also X-ray crystallography because the resolution is so good now. Confocal is also a little bit what I will touch. So confocal microscopy is where you basically illuminate through a sharp sample probe, also local illumination, where you can also overcome the AB limit. And then AFM well, can be operated in all conditions, but what is important in biology is, of course, liquid conditions. And resolution in XY is something like 1 angstrom, but that is of already very high resolution. But in Z-scale, it's amazing. It's 0.1 angstrom, the topography, and sample damage if you are careful not, and also pre-treatment. So it's in that way, it's also an easy technique. But I will come to many examples throughout this course. So, okay, that's again the summary here. Here the scheme again, and we are using in liquids, we are using the light detection mode, and we can topography relief. So with AFM, you always, I mean, it's a surface technique, of course. You get some three-dimensional information, but in the end, it's a surface topography relief what you get. So it's not three-dimensional in the sense of electron microscopy. You cannot go through the sample. And besides topographical information, also mechanical, electrical, and optical information. And one thing is also, because it's all mechanics, you can also manipulate samples. Yeah, so you can like lithography and things. That's also what you can do with AFM. Okay. Atomic resolution I already mentioned. Only if the surface is really atomically flat. I mean, there has been done a lot of research also to create sharp tips. Yeah, so this is with FIB, for instance. Then there was also a time when nanotubes were used for AFM, but that was only for a very short time, because nanotubes are very, very flexible, and this is, of course, also you need a kind of stable tip for that. But what is now, for instance, with the high-speed AFM, electron beam deposited tips, so basically where you grow a very sharp tip with an electron microscope on the AFM. This is maybe now the sharpest tip, which is also commercially available and used for imaging. You can see that here. So this is typically how cantilevers for AFM in biology look like. So that is this sharp needle electron beam assisted deposition. Here we really get the sharpest tip that is also shown here. Okay, so then we also know that it's of course a scanning technique, AFM. Yeah, so the sample has to be scanned line by line, and that is also why commercially AFM is a rather slow technique if you compare it with optical microscopy, where images are recorded by one. But I will also talk about high-speed AFM, where you can also really nowadays get really also fast images and even able to monitor dynamics. Then we have the laser spot here, and then also the feedback loop, which controls the whole sample. So basically, you can image with a constant force, and the tip follows the topography of the sample. And this is and what is also used is a 4-quadrant detector. Why? I mean, of course, for the topography, you basically just need up and down. But for instance, if you are interested in friction, then it is important to also have this detector. So because then I mean, of course, for topography, you measure the bending in the vertical direction, but for friction forces, it's a torsional bending of the cantilever, and then it is important to have two diodes there, and from there you can also measure friction forces, for instance. That's why this is now what is commonly used is a 4-photon detector. Okay, yeah. Important is, of course, also the scanner, which you need. So this is what you cannot do with a stepping motor, so you need something more sensitive. And this is why for moving the AFM cantilever up and down and also laterally, piezo crystal is used. And we know that piezos, when you apply force on it, it can generate an electric potential. But what is used for AFM imaging and force measurements is the inverse piezoelectric effect, that you apply potential and then the piezo can extend into C and into XY. And there's many, I'm not going into that, but there's many different configurations of piezos. There's stack piezos and so on, which is used for, well, depending on the company, of course, for different applications. Yeah. Feedback, of course, is important, because if you scan on a constant height, then there's different forces depending on how high the sample is that is applied. And particularly in biology, you want to be gentle and apply as less force as possible. And this is why the feedback loop is important, to keep the forces low. And then you get the topography relief from the movement, from the C movement of your scanner. Okay, contact mode again. I mean, it is used also in biology, and there's this was actually in the 90s. Some of the best images were actually also done with the contact mode, but this was often on kind of protein crystals in a way. Yeah, so like if you have a regular arrangement, like for instance purple membrane. I think purple membrane is maybe the most famous example, where you have a rather rigid membrane, and then it was shown that with contact mode you get actually the best resolution, a better resolution than in tapping mode. But of course time have changed, and I would say now the best resolution what you get now in biology is with a high-speed AFM. This is what I would, and the high-speed AFM operates in a tapping mode like configuration. Okay. Yeah, contact mode can also in biology be operated in the repulsive and attractive regime. But I have to say that most of the examples are in the repulsive regime, yeah? Because attractive interactions in liquids, they are of course diminished. Yeah, that has to do with the dielectric constant of water is much higher than in air, for instance. And usually also in biology, you have physiological buffers which contain salt, yeah, because you need physiological conditions, and then attractive forces are screened by the ions in solution, and this is why actually most often the repulsive interaction is used in biology. What is also important is the error image, yeah, because the feedback loop is of course not endless fast, yeah, so there's always a slight difference between the value that the feedback loop aims to reach and the actual value that is kind of limited by different time constants in the feedback loop. But we can also take advantage of that, because in a way then that is called error image. Oh, somehow it seems that the power not switched on my laptop?
How the electron beam used as a tip, and what coating material has been used to generate that kind of tip in the cantilever?
Well, I never did it myself, but it seems to be fairly easy. So what is actually used is kind of the pollution of the electron microscope. Although the vacuum, it's not perfectly clean, and this is then somehow deposited on the AFM tip. So it is with some experience you can actually do it. Yeah? So it's not it's not highly sophisticated science. But I cannot tell you voltages or experimental conditions for that because we are not doing it we are buying it. For instance, in the lab of Toshio Ando, who invented this high-speed AFM, they are doing it on a routine basis, and also students who visited Toshio Ando's lab could do it very easy. So it's and I'm sure it's also published somewhere, so you can find conditions. It doesn't seem to be very critical. Critical in the sense, yeah, of course, you want to get really a sharp tip, but actually, what you can also do, you can. I mean, the tips are also quite expensive if you buy them, yeah. But you can also clean the tips. Yeah? So also with the electron microscope, you can smash the EPD tip away and grow a new one. Yeah? So here you can. That's maybe an advantage. You can use cantilever multiple times. Yeah? Because whenever it becomes dirty, you just get rid of the EPD tip and grow a new one. So that.
Thank you.
Sure. No, it's just an electron microscope. You don't need FIB for that. Yeah, it's just done with an electron microscope.
So, Peter.
Yeah.
So you mentioned that water has high dielectric constant. That's why the attractive forces won't be there during the imaging.
I didn't mean it as strict. It's one of the reasons why attractive forces are diminished because of the dielectric. It's one reason.
But if we are doing it in air, then in that case, the attractive forces will be dominant, can be dominant.
Yeah. I mean, of course, you have also capillary forces then. Yeah, if you do it in air and not in vacuum, that is true. But capillary forces is also a kind of short-range attractive force in a way. Yeah, it can jump in and the capillary force is not really. You don't really have a stable force field with that, because what capillary forces do is that basically, okay, you have some. If you reach the hydration layer, yeah, it then jumps directly on the surface. So that is. So I don't think that capillary forces are really used as a force field to image in an attractive force field because it's a kind of rather unstable. It's a steep gradient when you reach the hydration layer, and the same is if you pull out on that. Then it's first you have the adhesion because of the capillary forces, and then it jumps back. So it's not really a smooth force gradient, and this is what you would need for stable imaging in the interactive regime.
Thank you.
Sure. So, as already mentioned, for biology, it is the mode that is often used is tapping mode, where we are detecting the amplitude, basically the amplitude reduction, because you can imagine when you're at contact with the surface that the amplitude is being reduced, and the cantilever amplitude is filtered out and goes to the feedback loop, and the feedback loop then works with the constant amplitude, and so same as with constant force, but just with a constant amplitude. And this is of course good for biological samples. So we can see that here that this is kind of the free amplitude. Yeah, so you oscillate the cantilever, and as you go into the surface, the amplitude is being reduced. Okay. And then you are choosing an amplitude reduction that is then held constant by the feedback loop, and the scanner goes up and down and holds the amplitude constant. That is how it works. So in principle, The forces that are acting in tapping mode consists of three terms. So this is the normal inertial force. Then what is also significant in liquids is the damping, yeah, because you're basically you're squeezing the liquids in between the tip and the surface, and this is actually also already active at rather high distances, yeah. So that is also micron distances. That is also something. And then, of course, the restoring force of the cantilever, and this is the excitation. And actually, also, if you're, yeah, and these are all the forces that are in principle acting on the cantilever in the tapping mode. Then there is also some phase shift, yeah. So if you're because you're with tapping mode, you're always working close to resonance, and of course, if you know mechanics, at resonance there's a phase shift of 90 degrees, yeah. So there's always also a resonance, and this is how that looks like. And actually, this phase shift can also be used for imaging, because it somehow also gives, not really quantitatively, but somehow also can give you some material properties, for instance. Yeah? Because if the tip sticks to the cantilever, then you have some more phase shift. It says something about the softness of a sample, something about the adhesiveness. Yeah. So you can also use the phase signal for imaging. And this is what you see here. And sometimes you get in the phase image a better contrast than in the topography image. That is also so kind of nice. For instance, also if you image material compositions, yeah, so different materials can have a different phase shift. That's also what can be used. And there's also frequency modulation that can be used. So mainly in biology, amplitude modulation is used. So the amplitude is held constant. But there is also an imaging method that holds the frequency constant. Yeah. This is not so much used in biology. It's more used in vacuum. Yeah, because in biology, of course, the signal is much broader. Yeah. And in vacuum, you have a very sharp, and then you can hold the frequency constant, because it's important to be there on where the slope is the steepest, and then it's the most sensitive. Yeah. I mean, there is some people also like imaging hydration layers who are also using frequency modulation, but this is rather kind of specialized there. So frequency modulation is not very much used. One thing that is certainly important in biology is the resolution, because we don't have atomic flat surfaces. So imagine this is a protein. A protein is maybe a dimension of 5 nanometers or something like this. And that is also the tip radius is maybe also in the range of 5 nanometers. And this is why if you image an object like this, what you actually get is something like this, yeah, because not only the very tip end touches the protein, but also the side of the tip already touches the protein, yeah? And that is also called tip artifact or tip broadening, which has to do with the similar dimensions of proteins and tip radii, for instance. And this is the formula how you can calculate this. So this is the full width at half maximum is then 2 times the d is the diameter of the protein, r is the tip radius, and this is how you can get this full width at half maximum if you know basically the tip radius, but you can also recalculate it. So if you measure something like this, and if you know the radius of the tip, then you can recalculate the true dimension of the protein. Yeah? So you can correct for that if you know the tip radius. But of course, the tip radius is not always so accurately known. I mean, the provider gives you some value, but that's also something what you can measure with a calibration grid. You could also measure tip radii, for instance. But this is certainly something which is an effect in biology. So we can see that here. Yeah, it depends on. Then artifacts, I mean, this is not specific now to AFM in biophysics, but what can cause problems is the non-linearity of the scanner, and this is also why you have to calibrate the scanner. Yeah, so this is, but there's also calibration grids available, and hysteresis. These are some problems that are accompanied with piezos as such, but this can be calibrated with a calibration grid. Okay, so that is basically what can be. Okay, and then just finally to show you one example of bacteria, how they are imaged, and just to show you that physiological conditions can be really important. So this is these are some bacteria, and this is what you get in dry environment. So it's not so bad, but with the contact mode. But if we measure the same bacteria in liquid with the tapping mode, we get a much better resolution. Yeah? And this is why physiological conditions are, because you basically you destroy biological samples. Yeah? If you dry biological samples, then you somehow destroy the structure. Yeah? And that is why it's so important to image biological samples in physiological conditions. And then, as already mentioned, but this will come in very much detail, is then force spectroscopy experiments. It will actually be the next lecture to tell you how we do this force spectroscopy experiments. So I will talk about, we need to do some tip chemistry for that, but this will come in detail in the next lecture. And there's also another lecture then on a derivative of force spectroscopy, which is topography and recognition imaging as a special application. But this will come in detail later. And just want to mention also that somehow a derivative, you may look at it as a derivative, is ENSOM, so near field optical microscopy, where you don't touch the sample, but you focus, confine the light in an aperture here, and then you illuminate just a very small area. And this is also a trick how you can overcome the Abbe limit, and this is also, so you have a near field now. And but what you have to do here is, of course, you also have to scan the sample, yeah, because you illuminate only in a very light area. Okay. But you can also get some very nice. And another derivative of AFM now, where we are using conductance, is actually the scanning ion conductance microscopy, where you may have heard about patch clamp. Yeah, so this is a technique where you can measure conductance through a cell, for instance. So you have you have a pipette actually with an electrode in there. And this is now used. It's to make kind of not. It's not a tunneling current what you're measuring. It's a real current. So basically coming from the solution. And originally the idea was to really probe ion channels with this, but this didn't turn out to work that well. Yeah, because the conductance for ion channels is very small. But there's also some conductance in the liquid. And now it is actually used as a topography imaging method, where you use, instead of a mechanical contact, the conductance between the electrode in the tip and the environment. So it's basically a contactless imaging method, which can be used in biology, and it works very nice for imaging cells, for instance. Yeah, this is just some examples. Yeah, and also just to complete, of course, you can also kind of misuse the mechanics of the AFM to do lithography. Yeah? So you can write structures into samples. This is also something what can be used. And there was this was also offered by a company, the so-called deep pen lithography. So where you can also write structures into biological materials, or even deposit material. Yeah? So there's also AFM tips available with the channel, and then you can deposit material on the surface. Okay, so this was just a first survey of AFM in bio, and we will go in detail into different modes in the next lectures. Okay, yeah.
Given that contact mode and tapping mode, both so while imaging your biological samples, both can be done in physiological conditions.
Right.
So why tapping mode is giving better resolution than contact mode?
It depends on, yeah. So well, if you have a rather rigid surface, yeah, then a contact mode can be better. Yeah? Like for kind of 2D crystalline structures, or like purple membranes, for instance, or S layers. Then contact mode can be better because you're not leaving the surface. Yeah? However, if you have a very fragile biological sample, it can be destroyed by force. And then tapping mode is better. It also depends on tapping mode is also not all the same. It's for instance with so the best tapping mode is the high-speed AFM, because there the amplitudes are very low, just 1 nanometer, and the amplitude reduction is just 1 to 2 angstroms, and that is of course very gentle. In conventional tapping mode, the amplitude is 5 to 10 nanometers, and then it's also a little bit destructive. And also the momentary force of the tapping mode is actually quite high. Because you also with the phase shift and everything, you're working resonance, so the feedback loop is limited. So the momentary force of tapping mode is higher than in contact mode. But you are not always pushing on it continuously, and this makes it then better. But it requires really a precise adjustment of amplitude reduction, and so on.
Thank you. Thank you.
So in tapping mode, how it's being make sure that the atoms are not getting skipped when it's tapping.
The atoms are not getting.
So how is it? So in contact mode, it's in continuous contact. So it is scanning each and every atom. But in tapping mode, it's for a moment it's skipping or it's coming in air. So
Yeah, but you are actually also not really, in biology, you're also not really scanning every atom. This is maybe shown here with the, because, you have here, and this is why for atomic resolution, you really need atomically flat surface, because then you have this one atom at the very tip end does all the imaging, and the other atoms never are touching the sample. But if you're looking here, I mean, imagine if you come with the tip here from the side, then of course already, if you come from this side, then already here the tip starts touching the probe, and also if it leaves. So in that case, it's a rather broad area on the tip that also touches the surface. So it's not really a single atom to atom contact. And of course, in tapping mode, you are also leaving it, but the frequency is very fast. So it's not that you are missing something, because there's the oscillation frequency is very high, and the line scanning speed is not so fast. So you're not missing anything. But in both modes, you don't really have single atom to atom contact in biology.
and also the d/2, the radius is the radius of an atom of a biological molecule, or it's the biological molecule itself, d/2.
I don't know. It's a biological molecule itself. So that is because let's say it's something. It's 5 nanometers. Something roughly. Tip radius is now the sharpest one. Is maybe, if it's not EPT tip, 2 nanometers to 10 nanometers. That's typical tip radium, and proteins are maybe from 2 nanometer to 30 nanometers, whatever. But let's say we are somehow in the 5 to 10 nanometer range, typically, if you're talking about single proteins and kind of commercial tips.
Thank you.
Can you please elaborate more on phase imaging and its advantages? We were explaining phase imaging.
Phase imaging, yeah.
Yeah.
Let's see. Yeah, this is somehow what defines the phase. So the phase somehow it is of course also because you're using a tapping mode in resonance, and then per se you have a phase shift of 90 degrees. That is just because this is just how the resonator works. But then what you can detect with a phase image is basically two things. That is the softness of a sample, yeah, because then you get some additional phase delay, and also adhesion. Yeah, so if the tip adheres to the surface, then you get an additional phase shift.
Yeah.
Yeah, so that is, but that is what you see here. So this is, for instance, here this is two materials, yeah, and you don't see a lot in the topography image, but the phase image is much better because you get a different phase delay from the two materials, yeah. So this is one, you can get a very good material contrast, often if it works, yeah. But somehow, I mean, of course, you can also measure the phase quantitatively, but you don't really get a Young's modulus out of it or so, yeah, because it's depending on so many parameters. Also, the tip radius plays a role on the phase shift, yeah. So it's good for getting, it's nice for getting a good contrast, but you cannot really quantify a physical parameter. Although you can quantify the phase image, but it's too complicated to get a quantitative physical parameter.
Next question is like you told us frequency modulation are now not in use for I think in tapping mode.
In liquids, not used with liquids, not so often.
Yeah, so why is that? And
Yeah, because you can see here this is the resonance curve, yeah, and the difference between air or vacuum and liquids is that in liquids the resonance curve is much broader because of the damping, yeah.
okay.
And then of course because it should be done at the steepest slope, because then you have then it's most sensitive, yeah, and because it's so wide and so flat, it's just much less sensitive than in vacuum or in air.
Thank you.
Sure.
Can we detect mesophase changes or phase changes using the phase imaging?
If you can detect
Phase changes, if there are any phase changes in the sample.
if we can detect that, or
Yes.
yeah,
Using phase imaging, can we detect different phases of the sample?
uh, yeah. I mean, it's good for contrast, as you see here. Yeah. So these are two different materials, and the two materials result in a different phase shift, and that's why we get a nice contrast here. So you get a phase image you always get for free, basically. Yeah, it's a channel, and it always, you can always detect it. Yeah? So it's for free. You don't have to do something special for it. You can always detect it. The question is, where does it make sense to record it? But you always you get it for free. So typically in tapping mode, you have the the topography image. This is with the feedback loop. Then you have the error image, which is the difference, because the feedback loop is not endless fast, and the phase image. You could also record the torsional image, but this is not important in tapping mode, because you're oscillating. This is more in contact mode, but you also get for free the torsional image. You don't have to do anything on top of that.
cell culture or something, there are very little phase changes also, like that, from solid to liquid, liquid to gas, those phase change. So those transitions.
Uh,
So those transitions that we that happens inside the cell or inside the sample, can we detect that also by analyzing the resonance, change in resonance?
Yeah, I mean, AFM is of course a surface technique. Yeah, so basically you're sensing the surface. Yeah, but for instance, on cells, yeah, you have like underneath of the cell membrane there is a cytoskeleton. Yeah, like for instance actin fibers, and there you get also some mechanical information. Yeah, which you also see topography or error image, but also in the phase image. Yeah, that's also something for for kind of different mechanical properties of locations give also some. So I would say you can see if you image a cell, then you would see the actin filaments also in the phase image. Yeah,
Okay,
because
okay.
there's a different mechanical response. Yeah. Uh-huh. And then